Hey everyone. So welcome back to this series on deep learning. And in this lecture, what we're going to do is look at logistic regression, but in the context of a neuron and a neural network. Right? And so we've previously seen how a single node or single neuron model would work, right? You have a simple neuron where initially you have the linear part of the neuron where the inputs come in. And then you have weights here and a bias, which are the parameters of that neuron. And that is what is trained. The inputs are multiplied by the corresponding weights. The bias is added. And then what you get is an intermediate value Z, which then gets passed through the activation function. And what we did previously was use a ReLU activation function to get the output of the neuron. And what we did was train this for a simple regression problem where we were trying to predict prices, right? So we've seen that context and that correlates to linear regression, right? But now another topic in machine learning that is very, very key is logistic regression. So, well, what is logistic regression? First of all, let's look at what a logistic function is. So if you take an input value Z, and then you say, actually, you take that Z and say 1 by 1 plus e to the power of minus Z, where e is the exponential. The function you get is the logistic or the sigmoid function. So what does this function basically do? Well, given an input value Z, and Z could be any value, we've plotted it here from minus 10 to 10, we see that it takes that input and converts it into this plot, right? So what's that plot doing? We see that for very small, or rather very negative values of Z, anything, more negative than even minus 7.5 is effectively being kind of set to zero, right? And this is not exactly zero, it's getting to zero, but it's very close to zero. And then as we come closer and closer to Z being zero, we see that the value of the function, and we're calling it A of Z here, is coming closer and closer, right? And we're calling it A because it's the activation function. Technically, for a sigmoid, you use the sigma notation, right? But I'm using A here simply because we're going to use it as an activation function here. So as you come closer to Z equal to zero, you see that the value of A, or rather sigma, comes closer and closer here, becoming larger. So the function is active, right? It is changing. And then as the value of Z becomes very, very close to 5 and goes further than that, the value of the function, of the logistic function or the sigmoid function, becomes 1. So what you see is it takes the input and squishes it so that the output is between 0 and 1. Now, because we're looking at this from the context of machine learning, and in this case, from the context of deep learning, we need to know the sensitivity of this, right? So the A of Z is 1 by 1 plus e to the power of minus Z. Compute the derivative of that with respect to Z. What do you get? D by dz, or 1 by 1 plus e to the power of minus Z. Now, if you remember the quotient rule of differentiation, we've covered that in the supplementary lecture on differentiation. It's basically the denominator squared, and then the numerator, if it's u by v, it's v du minus u dv. And so d by dz of 1 minus 1 d by dz of 1 plus e to the power of minus Z. Now, as you can imagine, d1 by dz, derivative of 1 with respect to Z, there's no dependence, so that goes to 0. Here again, you have d by dz of 1 plus e to the power of minus Z. So d by dz of 1 is 0, and d by dz of e to the power of minus Z is minus e to the power of minus Z. So what you end up with is the first term going to 0, and the second term being minus 1 times minus e to the power of minus Z. And then the denominator is 1 plus e to the power of minus Z squared. And so you can just simplify, you just take the, negative and negative is positive, and you're left with this. Now what we can do a small manipulation to this expression. We can say, what if we add 1 and subtract 1? So it's 1 and minus 1, which means it's actually still e to the power of minus Z. But what this allows us to do is now separate this into two parts. You can have the 1 plus e to the power of minus Z by 1 plus e to the power of minus Z squared. And then minus 1 by 1 plus e to the power of minus Z squared. Okay. And now 1 plus e to the power of minus Z by 1 plus e to the power of minus Z squared. Well, you can just, you can simplify this as 1 by 1 plus e to the power of minus Z, right? This is the power of 1, it's the power of 2. So you can simplify that. Why do we keep it in this form? Well, 1 by 1 plus e to the power of minus z is a, right? So what does this become? It becomes a minus a square, where a is the output that the sigmoid function gives you. And so what are you left with? You're left with a times 1 minus a, right? Or a minus a square. So you're left with a very interesting expression right here, because it's now the derivative of that function is actually can be written in terms of that function. We have seen this previously with the tanh function as well. So that means it becomes very suited to being a neuron in a neural net, right? Because you can do the forward pass, get the value a, and in the backward pass, you can use that a to compute the derivative, right? The local derivative. Then use chain. Okay. And so for our, for this particular lecture, well, we know it's a single neuron model. So the output, if this is the activation function, then you can say the output y hat is equal to a, right? And so you can also write it as y hat is 1 minus y hat. This is only if it's the last neuron, or in this case, it's a single neuron model and it's the last active, it's the activation, right? Why are we writing it in this form? We'll see that in a bit. And so if you plot the derivative, you saw that the function, the actual sigmoid was going like this and then becoming like this. So going from 0 to 1. You see that the derivative is similar, only it kind of is 0 for very negative values and for very positive values. And as the value comes close to 0, the derivative peaks. What does this tell us? Well, so backpropagation is how a neural network is trained, right? We're focusing purely in terms of the context of a neuron. But basically what you see is this function, right, is active and the derivative is active in this region. So what it means is if your inputs to that neuron are very, very negative or very, very positive, the gradients are going to be zero, which means it's going to get complicated to train the neuron, right? Because the gradients are going to be very small, which means when you update the weights, it's not going to get updated by a lot. And if it's very negative, even with those small changes, it's going to take a really long time, or it's not going to converge, right? Um, on the other hand, if your values or inputs to this activation function are closer to this range, ideally somewhere here, then you can see that the gradients are quite large, which means the backpropagation will update the weights fairly quickly, and so the neuron will get trained better, right? So it's something you need to keep in mind when you use a sigmoid activation function. So what we've done, taken the previous kind of neuron structure, but now we have replaced the ReLU with the sigmoid activation function. And so you're left with Z is sigma WIXI plus B. Y hat is A of Z plus 1 by 1 plus e to the power of minus Z, right? So what do we use this kind of function for, and what are we trying to do with this neuron? So previously what we've done is used it for regression, right? Where we're trying to predict a value. In this case, we're looking at a classification problem. And so what we're trying to do is predict, and it's not a value technically, it's predict between two or more classes, right? So for example, you have this image of this, dog. What you're actually trying to ask the algorithm is, say you have three classes, and you have images of horses, cats, and dogs. And then you're going to train the algorithm so that when this picture shows up, it actually says, oh, actually, this is a dog, right? So that's a classification problem. Now, a binary classification problem, which is what we're going to look at today in terms of an example, is where you have two classes. Right? So you're trying to pick which of the two classes it is. So you could actually say, is it a cat or is it a dog? Right? One of the two classes. Or for example, you could have yes or no problems, right? So is the email spam or not, right? Is the sentiment of the review positive or negative? So problems like that are binary classification problems. And that's where a sigmoid function becomes quite useful, because as you can see, the output is between 0 and 1, right? And so if that's the last kind of neuron, or in our case, it's a single neuron, right? So it's the activation function. You can think of it this way. You can think, given two classes 0 and 1, right? These are the labels, right? So classes 0 and 1. You can say y hat, which is the prediction by that neuron, is the probability that the output, right, is the probability that the output is class 1, right? Which means you can say 1 minus y hat, because there are only two classes, 1 minus y hat, basic probability, has to be the probability that the class is 0, right? And so now what you can say effectively is this function is kind of trying to predict whether the output is between class 0 and class 1, right? And so what we can do is to train this neuron, we need a loss function, right? So given we say that the neuron is trying to predict, giving you a value between 0 and 1, and we're saying that what if it's the probability? So what if y hat is the probability of the class being 1, right? Then how do we treat the loss, right? Because to train the neuron, you need a loss. So let's just assume there are multiple data points, but we're looking at one data point j, and it can either be 0 or 1. So the label is 0 or 1, which means y is 0 or 1. If y is 1, we're saying we are saying that let the probability that y is 1 for the data points picked, and the parameters are w, right? The neuron is w1 x1 plus w2 x2 plus so on plus b, right? It could, yeah. So for those parameters, let's say the probability is y hat, which is the output of the neuron. Right? Hopefully this makes sense. Which means the probability that it is 0, because there are only two classes, right? There's only 0 and 1. So the probability that it is 0 is 1 minus the probability that it is 1, right? For the same kind of inputs and parameters. So it's 1 minus y hat. Okay. Now what are we trying to do? We're trying to get a more general version. So if we say probability of y given x and for these parameters, well, you can write it as y hat times y hat to the power of y times 1 minus y hat to the power of 1 minus y. Why does this work? Because if we know y can either be 0 or 1. When y is 0, right, y hat to the power of 0, this term becomes 1, right? Anything to the power of 0 is 1. And we're left with 1 minus y hat, because 1 minus 1, right? We're left with 1 minus y hat, which is this. 1 minus 0 is 1, right? So 1 minus y hat is this. On the other hand, if y hat, or on the other hand, if the label y, right, is 1, then y hat to the power of 1 is y hat. 1 minus y hat to the power of 0 is 1. You're left with y hat. So this effectively reduces to this, to these two cases, right? And these are the only two cases that are possible. Now, so this becomes a general way to define this probability, right? Now, what can we do? We can take the log of this, right? So we say log of p is log of this expression. Now, you look at the basic rules of logarithm. You say a log to a base b of a product of two terms can be written as the log of base b, the first term, plus the log of base b, the second term, which means you can write this as log of y hat to the power of y plus log of 1 minus y hat to the power of 1 minus y. Now, again, here, just a reminder, y can either be 0 and 1. And y hat is the output of the neural network of the sigmoid function, right? Which means y hat can be between 0 and 1, right? Just to be clear. Now you have this term, what happens? Let's use another rule of logarithms, which is the log to the base b, x to the power of y is y times log to the base b x, which means you can take this y outside and say this actually becomes y times log of y hat plus 1 minus y times log of 1 minus y hat. So we've got this in this form, right? Now, we've got this in this form because it's easier to now optimize this function than it is to optimize this, right? Now, if this was a machine learning context, you were learning logistic regression in, what you do is now use the maximum likelihood estimation, which is an approach used in probability, which would try and find the W, the parameters W, that would maximize this probability. Right? So this is called the log likelihood, and we try and maximize that. Now, and now what we are going to do is we're using it to train a neuron, and we're using gradient descent. So there you would be maximizing, which means you would use gradient ascent, right? So if you can take a reference of machine learning, and we'll have a course on machine learning later, so you can check that out as well when we get there. So you would be maximizing this. We want to use gradient descent to train a neural network or a neuron, and we're using this in that context. So we want to minimize it, which means what we're going to say is we're going to say the negative of y log y hat plus 1 minus y log 1 minus y hat is our loss function. And I've said here it's for data point j. I've just omitted the subscript to make the whole thing simpler, like the notation. So this is for one data point j. What we can do now is this is for a data point. You do what you do typically. when what we did with the mean square error as well. We take this for a data point, but now we sum it across the different data points and we divide by the number of data. So effectively averaging across the different data points. And so what this is called is the binary cross entropy loss. And if you take a more general classification problem, which we will take up when we kind of get to a full neural network in a couple of lectures, you would have a cross entropy loss with multiple classes, right? So an NN cross entropy loss. So now what we're going to do is just look at this a little more carefully. So I want to find the error, or how the error or the loss for that matter is going to show up, right? So when the label is zero, what happens? When the label is zero, this term is supposed to go to zero, right? Y goes to zero. This goes to zero, and this is 1 minus 0 is 1. So you're left with log 1 minus y hat and the negative sign, right? And so if y hat is 0, right, meaning the prediction and the actual label are the same, this would go to 0 and you would be left with E of w is minus log 1, which is 0, right? So if the prediction is correct, your label is 0 and your prediction is 0, the error is 0. So the loss for that data point is 0. Same thing here. What if you have a label of 1? The label is 1. This y is 1, which means this term is log y hat. This y is 1. 1 minus 1 is 0. This term goes away, right? What you're left with is minus log y hat, right? What happens if it's predicted correctly? The error now is minus log 1, which is 0. So we see that this loss function gives the right error values, right, if the prediction is correct. And if not, then you will get an error, right, because this will not be 0. Okay. So we see that the loss function is makes sense. Let's now get the derivative because we need to trade this. So the derivative of the loss with respect to the prediction y hat, which is what we care about, is d by dy hat of this. Now y is not dependent on y hat, so you can come out of the derivative. You're left with d by dy hat of log y hat plus 1 minus y times d by dy hat of log 1 minus y hat. What's the derivative of log y hat? It's 1 by y hat. And what's the derivative here? D by dy hat of 1. You can say let z is 1 minus y hat. And so you can say d log z by dz times dz by dy hat, right? Using chain rule. So the derivative of basically dz, but d log z by dz would be 1 by z, which is 1 by 1 minus y hat, times the derivative of 1 minus y hat by y hat is minus 1. So you're left with minus 1 by 1 minus 1. And so you can rearrange this to be minus y by y hat, right? This minus comes here. So it's minus 1 minus y by 1 minus y. You can use this expression. I'm just kind of simplifying it a little more. So you multiply this 1 minus y hat here and this y hat here, right? Which is what we've done here. You simplify the expression. This y hat and y hat y cancels. You're left with minus y minus y hat by y hat into 1 minus y hat. Why have I got to this point? We'll see in a minute, right? So we've got this sigmoid logistic neuron. The loss function, the activation function is the sigmoid. Now for the linear part, we've already derived this in the previous session, with the single neuron for regression. So we know the derivative of z with respect to wi is the xi. The derivative of z with respect to the xi is the corresponding wi. The derivative of z with respect to b is 1, right? So use chain rule. We want the derivative of the loss with respect to 3 parameters. What are we going to do? Well, we have dl dyj, which we just computed, times you multiply that by the derivative of the sigmoid function dyj dzj. What do you get? dl dyj times dyj dzj is dlj dzj, right? Ljj just indicates the data point. So you get that. And then you multiply by this derivative dz dwi, which we already have from the previous lecture. You end up with the derivative of the loss with respect to the weights and the y's. Right? This should be zj for the corresponding data point, right? So we've just computed this, right? I've just removed the j here because it is for the j data point. We've computed the derivative of this function. and we've computed the derivative of xi. Because this is the neuron here, this is the activation function. Right before the loss, the output yj is the output of this activation function, right? Which is why you can write this, it's actually a into 1 minus a, but because in this case a is y hat, it's written as y hat. What does this do for us? You see that for this single neuron, these two terms cancel, and what you're left with is minus y hat times xi. So if we wanted, we didn't have to do the full backward pass. We can just compute, get the derivative directly, and just keep updating, right? We know dl dwi is this. What if it's with respect to b? Well, if it's b, the xi is 1, right? That's it. Now, we are going to implement this as a neuron. So when we implement this, we'll actually implement this term in the neuron and this term in the loss. But actually, if you were doing this, solving this as a machine learning problem, you would actually get this term. Only it would be, a maximization problem in machine learning context. So the negative sign would not be there. You would use gradient ascent. We're using gradient descent, and we've got this term. We'll actually implement it like this. Okay. And then what you do, you have a decision boundary. So once you've got your prediction for training, the loss function is great. But now how do you know, once you've kind of trained the model, you want to predict the class, right? So you want it to say class 0 or class 1. So what do? You say, well, set up the decision boundary. Let's say 0.5 is the decision boundary, which is a good estimate. So if y hat is greater than equal to 0.5, the prediction is 1. Else the prediction is 0. Simple, right? So what you're getting actually is a probability. You're saying if it's greater than or equal to 0.5, the prediction is 1. This should be greater than equal to. And if it's less, then the prediction is. Okay. So let's go implement this. So we're going to have this classification problem. It's got two features or two inputs. So x1, x2 is feature 1, feature 2. And two classes, there's the red and the blue. And we want to see how well this neuron set up for logistic regression is going to do in terms of classifying. So given the data, is it able to predict correctly which points are red and which points are blue? So the parameters that you can train are W1, W2, and D, right? And we've already set up gradient descent. So we're going to use this as the loss function that gradient descent is going to minimize, right? Right. And what we're going to do is at each iteration, we're going to have an initial guess first of the parameters. And then based on the gradient at that point and the learning rate, we're going to keep updating the W's till it converges to the solution where the loss is minimized. So we know gradient descent quite well. We have covered it. If not, do go check out the lecture on gradient descent. But I think we're ready to now go and implement this. Okay, so let's open our Jupyter notebooks and get going. Okay, so hopefully you've loaded up your Jupyter notebooks, and let's get started. So for this, what we have is we obviously have the math module. We've got NumPy, which we're importing as NP. We've got Pandas, which we're importing as PT, and Matplotlib, where we're going to use PLT. Right now, a lot of this notebook is very similar to the single neuron for regression case. So what I've done is kept, instead of rewriting or writing this from scratch, I've actually kept some of the snippets, right, and modified it a bit so that we don't waste time rewriting stuff that you already know how to do from that lecture. And then we'll just write the parts that are new, right, that we need to learn how to write. And we'll leave the stuff that we already have done in the previous lecture. I've already put it in. The first thing is we want to load the data set. So there's a file for classification 2D example. It's a file that we've prepped for this example, and with the code, I'll make it available. So you use pandas. You say df is pd.read CSV. What pandas will do is read the CSV file, which is something it's a file format if you're not familiar with it, something that you can export from something like Excel or Google Sheets or something like that. And then it's a very simple, it's just comma separate. Right? So it's very easy to use. Stores it in the DF. And if I just run this, right, well, I didn't run the first imports. So the imports, and now I run df.head. And so it shows you the heads, right? And so you have feature 1, you have feature 2, and you have the corresponding classes. Okay, so Now what we are going to do is we are going to visualize the data. Right? So we're going to say, right? And so what I've said here is the color is blue if the label is class 1, right? The labels are class 1 or class 2, and it's red if the label is not blue, right? Because there are only two classes. And then what I'm plotting is feature 1 and the feature 2, right? So plt.scatter is a scatter plot. It's just going to print the values of, well, the x-axis is feature 1 and the y-axis is feature 2. And it's going to use these colors. So if it's class 1, it's going to show it in blue, and if it's class 2, it's going to show it in red. Okay. So we see that, and we see that there is a bit of an intersection, right? Okay, good. So now what are we going to do? We're going to take this data and we need to scale this, because as you can see, the axis is between 4.4 and 5.8. And here it's between 1.4 and 2.2. So we need to scale it up to be between, ideally between -1 and 1, right? Because we're using the sigmoid function. We're going to try and make sure that we try and hit that, the, the part of that function where the gradients are active. So what I'm going to do is, as you can see here, I've taken the x, right, which is the inputs, to be feature 1 and feature 2. So what this will do is take feature 1 and feature 2 and take those values and store it in x. And y is the class type, right? And then what I'm going to do is I've written a small label encoder. Now, typically when we'll do this later, when we start using things like PyTorch, there are functions there which will automatically encode this into 0 or 1 and so on. What we want to do is we want the labels not to be class 1 and class 2. We want it to be 0 or 1. So I've written a small function here called label encoder. We've taken these labels, which is just these values, and what it will do is say if the label is class 1, the value is 0. Else, if the label is not class 1, which means it's class 2, the value is 1. And it'll store that in y, and we return y to be y. So it's just taking class 1 and class 2 and saying 0 or 1. Right? And then what I'm doing is I'm taking the x axis, right, which is between 4.4 and 5.8. And what I'm doing is I'm saying, well, actually, take the value and subtract 4 from it, which means you will get anywhere between 0.4 and 1.8. You divide that by 2, right? And then what you do, so what happens is that scales it down to be between 0 and 1. And then what I'm doing is I want it to be between -1 and 1. So if it's between 0 and 1, I'm making it between 0 and 2 by multiplying by 2 and then subtracting -1. So anything that is 0 will go to be -1. And anything in this case that's at the limit, right, will go to be 1. So I'm basically taking the data and scaling it up to be between 0 and 1. So let me run this function and run this as well. We also know that there are 400 data points. This is a function we've taken pretty much from the single neuron model lecture. We're saying, well, actually, I want, there are 400, so I'm taking 80 of those points. Now, typically in machine learning, in modern machine learning, you would have a train and then a test set, right? And so what we're doing is, what you could also use is a train, an eval, and a test set to do, which is what is done more recently. But I'm just sticking to training and test set because it's a very small data set, so that's easier to do. And so what I'm going to do is pick randomly. I know there are n total points. I'm going to pick 80 points randomly, right, without replacement, which means if it picks a point once, it will not pick it again, right? And so those are my test points. And then what I'm doing is I'm saying X test is those indices, and the training is everything but those indices. So it's going to delete everything but those indices and store that in train. Similarly, the same thing for Y. The test indices go to Y test, and the indices that are not the test indices go to test. If I run that, these are the indices that are going to get stored as the test data points, and everything else is our training. Okay. Now, I'm just visualizing X array here. simply, so we know which class these data points belong to, but just to make sure we've got, after scaling, it's between -1 and 1, but it's the same data point, it's the same distribution, right? So we've scaled it down, we've broken it into a training and a test set. Everything looks okay. Let's now go and take a neuron. So this is basically the neuron from the previous lecture again. I've not rewritten the neuron. I've taken that and we're going to modify this, right? So we're going to say there's a tag that you can give. You can pass in the weights and the bias. And then a lot of these inputs, which will come in the forward pass, these values, the X is the input, A is the output, and Z is the intermediate value. And the derivatives, we're going to store that. So we're just initializing it and setting it to 0. We also setting it to none. What we also have is an update weights function. So when we optimize, we want to update the weights. What you can do is pass in W, and in the optimization gradient descent, you're just going to have a single vector, right? You're going to have W1, W2, and B. So you can pass that in, and then what this will do is take the first two values and pass it to W, and take the last value and give it to B. Okay. So let's write the forward pass. So the input X comes in. We're not vectorizing over the inputs. We're just assuming that we're going to pass in each input one at a time, each set of inputs, right? One at a time. So you're getting X, which will be two values, X1 and X2 in our particular case, right? And so Z is basically W1 X1 plus W2 X2 plus B, right? So this is W1 X1 plus W2 X2 plus B. And so what we're doing is saying numpy dot Wx. What that will do is W1 X1 plus W2 X2. And we're adding B, which is the bias to that. Now what we need to do is implement the activation function, which is the sigmoid activation. So what is the sigmoid activation function? We've just seen it in the class. It's A is, so let me just, A is 1.0 by 1.0 plus numpy.exp, which is the exponential, right, minus z. 1 by 1 plus e to the power of minus z. Simple. And that is the forward pass. We're storing X because we'll need this when we compute the backward pass, what the input to that neuron is. We're storing Z as well. It'll help us visualize if we want to, and we're storing A because it'll help us again in the backward pass. So that's the forward pass. It's very simple. Now the backward pass. So what gets passed into the backward? Single neuron model, and whatever it is, the neuron basically gets the derivative of the loss with respect to the output of that neuron, right? That's what's passed back in back propagation. So what are we going to do? We are going to first write the derivative of this activation function. Now, if you remember, it was just A times 1 minus A. So what are we going to do? We're going to say dA by dz, which is the derivative of the sigmoid activation function, is just self dot A times 1.0 minus self dot A. Simple. We've already seen this in the theory part. And then what are we going to do? We're going to use chain rule to say we want the derivative of the loss with respect to Z. And so what is that? That is dL dA, which is being passed in, times dA dz, which we've just computed. Just going to remove this piece. What happens next? This is exactly the same as the neuron for regression because it's just the linear part of the neuron. And so dz dw, well, the derivative of z with respect to w1 is x1, with respect to w2 is x2, right? So it's just self dot x, right? Because x is x1 and x2. The derivative with respect to w now of the loss is just chain rules. You take dl dz and multiply by dz dw. With b, we know that the derivative of z with respect to b is 1, right? Sorry about that. Okay. And then the derivative of the loss with respect to b, chain rule, dl dz times dz db. So actually, you could just leave it as dl dz, but I'm just doing this so that you can see the steps. And finally, this again is something we don't need because we don't need the derivative with respect to the input, but doing this will help us when we start kind of assembling a neural network. So dz dx, which is with respect to the inputs, is basically, well, dz dx1 is w1, dz dx2 is w2, right? Because it's w1 x1 plus w2 x2, right? And so it's basically just the weight vector. Again, as you can see, this is quite simple in this case because it's just one neuron, and so it's just one set of weights. When we have a layer with multiple neurons, now you have to start thinking about different weights for each neuron, and so how would that come, right? So we'll get to that. And then the L dx, we only care about the derivative with respect to the loss, right? And that's the beauty of it. That's why chain rule really works, because now we can take dl dz times dz dx to get dl dx. Now what I'm going to do, I want to pass back, when I train this with gradient descent, both the derivative with respect to the weights and the bias. So I'm going to say numpy.append, and first the dldw, which is the derivative of the loss with respect to the weights, and then dldb. So it will create a vector which now is dldw1, dldw2, and dldw and dldb. So it creates a vector like this: dldw1, dldw2, dldw, and dldb, or rather numpy array, right? And then that is what we pass back along with the dldx, right? And we don't really need to worry about dldx here because it's single neuron, but I'm just passing that back, keeping it consistent with the previous lecture. We're also storing these in case we want to visualize this. So that's our neuron, plain and simple. We can just test it out quickly. We can say n1 is equal to, and I think I've called this neuron, right? Okay. So I'm just going to say n1 is neuron, right? And the tag is, so I have to pass in a set of weights. So let's just see. I'm going to say 0.2, 0.1. I have to pass in a bias, right? And so let's say 1, right? Or 0.3, let's say. And the tag is logistic. And I have not run cell above, so it doesn't know there's a neuron. And we've got that. So it's basically set up to work. Let's check out the forward pass. So let's say inputs. So X is np.array. And we're just going to see if this works. We're going to say 0.2, 0.1. And let's just, let's say n1 dot forward, okay, and give it the inputs X. And what we're getting is y hat. And we're going to say print y hat. And it gives you a value 0.58661. We can check if this is correct. It's quite simple to do that. What do? You know the weights. So let's just say 0.2 times 0.2 plus 0.1 times 0.1 plus 0.3. What do we get? We get 0.35. Now we're not done. Remember, we have this is z, so this is z is equal to that. And then what are we going to do? We're going to pass this through the logistic function. So we're going to say 1.0 by 1.0 by 1.0 plus np.ext and z. Run that. Oh, it's minus z, my mistake. And we've got the same value. Okay. So we've done that. So we know the basic implementation is correct. We can also just check if the backward pass runs. And so we can say now we've got n1 forward. Let's say dl dx, dl the a is, so say it's a numpy array. It's always good to say numpy array so the calculations will be done properly. I'm just going to give it a loss of 0.5. And we're going to say, well, we are returning dl dx, dl dw is equal to n1 dot backward. And we're giving it dl dA. And let's just print dl dx, dl dw, say go, and you will get this. Okay. So basically works. We know that it's giving us the derivative with respect to x and with respect to w. You can go try and check this out. That's an assignment for you. But basically, the neuron is live. So what are we going to do next? We are going to now set up the we've got the neuron, right? What we need now is the loss function. So we're going to use the binary classification loss or binary cross entropy loss. I'm just calling it binary classification. What does the loss function do? The loss function takes in the label and the actual prediction y hat, which we've just got here in the forward pass, and it returns the loss, and it also returns the derivative with respect to the loss. Now, actually, what really matters is the derivative, but we want to print out the loss. So we're going to say loss, right, is, and it's, what is it? If you remember the value from the lecture, np dot log y hat, right? And then you have, so there's a bracket here, and then you have plus 1 minus y, and let's make sure we get this right, times log 1 minus y hat. So that's the loss. And then we have the dl dych, the derivative of the loss with respect to y hat, which again we have implemented. So we've already computed that quite well. It's y minus y hat by y hat, right? And there is, so it's y hat times 1 minus. Okay, so that's that. And then what do we have here? We can just store this locally in case we want to check it out. And we are returning the loss and the d. I'm going to do one small correction here as well. I'm going to say define an epsilon is 1e minus 9. Why am I doing that? Because the denominator here, y hat and 1 minus y hat, what happens if y hat is very, very, very small, right? The derivative can blow up. If it's 0, it becomes infinity. So I'm just adding a plus EPS here and a plus EPS here, so that if for whatever reason the y hat becomes extremely small, it would indicate that you have a problem. But in the event that happens and it is not really a bug or a problem, the epsilon, which is 1e minus 9, so it's very small, will make sure the denominator doesn't go to 0, right? Okay. And we know y hat cannot be negative. It's a prediction, it's a probability. Okay, so we've implemented the binary classification algorithm. Let's test if this works. I'm going to say loss f is binary classification loss, right? And then we're going to say loss f eval, and let's say, for example, the label is 1.0, and let's say the prediction is 8, right? And it's, what does it return? It returns the loss and the loss, right? Okay, so let me just print this. Print. You get the loss and a derivative. So it's saying there's a loss of 0.22. What happens if my prediction is a lot worse? Right? I'm saying the label is 1, but the prediction is 0.4. You imagine the loss goes up. We're trying to minimize the loss. The loss goes up. So we've basically got the implementation. Okay, good. What's the next step? Let's go train the neuron. So already set some of this up. You've got a model, which is basically the neuron. I've given it an initial set of weights because I have a basic idea where this is going to converge to. So to kind of speed things up a bit, we're saying the neuron's weights are -5 and -4. And the bias is -0.3, right? And then we're setting up the loss function, which is the binary classification. So let's run this. So W is basically initialized to the same point. We're saying the learning rate is set to 0.05, training on the training set, and I'm running it for 7,000 reports. It's quite a bit. So what are we going to do? We are going to set this up now. So we're going to say, these are just for monitoring. We've done this in the previous lecture. Basically, we're saying we're doing batch training or batch gradient descent, and the batch size is the full training set, right? So because it's a small training set, so 320 points. So the batch size is the full set. Now, what we're going to do is the number of iterations. So basically that we care about is each iteration where the update is happening is the number of epochs. We're saying that we also want an array called the history of the weights, which is the number of epochs, and then the dimension of the weights. Same for the loss. We're creating a sum array for the weights, right? And we're saying setting this to 0 because when we run this, we are actually looping over the training data and each time computing the derivative for one data point and then adding it up and dividing it by the number of data points, right? Now, when we cover vectorization in a few lectures, as an example, we'll just take this and we'll vectorize this. So we'll take away this loop called xtrain, right? And we can just vectorize the operation. But for now, we have a little vectorization in terms of using np.dot and so on, but otherwise we're going to loop over the data points, right? Okay. And so I'm just updating W. I've set W here. I'm just making sure the model is using that for the first iteration. I loop over the number of epochs. Total loss is set to 0 for each epoch, and the sum of, or rather the mean actually, of the weights, of the derivative of the weights is also set to 0. I loop over the training set and I say X is X train. So for each data point, the X is the training X and the Y is the training Y. Now let's call the model. So what are we going to do? We're going to say Y hat is model dot forward, and it takes in the inputs X. Then what you do, you've got Y hat, which is the prediction, right? So what do you need? You need the loss function. So you're going to say loss. The loss is loss function dot eval. And what do you give Y and Y hat. And then what you do, you've got the derivative of the loss backward pass, right? So we get dl dx, which we don't really care about, and dl dw, which we really care about. And that's model dot backward. And we're passing it the derivative of the loss. It goes through and you get the derivative of the weights. To get that, you basically divide that by the number of data points. And the total loss is the total loss by n, right? Okay. So that's good. We're saying W history for each data point. If after at the end of the epoch, you're just storing the weights for that epoch, right? And the loss, and then we are updating. So this is the gradient descent step. We've seen this quite a few times by now. And once you do the gradient descent step, you get the updated weights. And what do? You update the weights, right? You update the model and you run this again. So let's now run this, right? And then see what it converges to. Okay, so I said 7,000 iterations, but I've actually run it for a lot more. I've run it for 14,000. And so we've seen that it's finally starting to converge. You look at the values here and you see that you're getting the decimals are starting to converge. Now you can try running this a lot longer, but we see that the basic model is starting to converge. So what we're going to do now is check the accuracy. So we did this in the previous lecture as well. I'm going to take the test set, and what I'm going to do is I'm going to say X test and Y test. I'm going to loop over the test points, evaluate Y hat, and now I'm adding here what is called the decision boundary. So what it's doing is it's taking the prediction. The prediction is greater than or equal to 0.5. It's going to say, yes, prediction is 1, or rather the class is 1. And if not, it's going to say the class is 0, right? And so what we're going to do, we're going to run this on the test set. So we see that, say for here, this is 1, it's saying 0.78, which means it's predicting correctly. In this case, it's 1, it's 0.99. So again, predicting correctly. In this case, it's 0, it's 0.61. So not predicting correctly. In this case, it's 1.98 correctly. In this case, it's 0 and it's 0.03. So it's predicting class 0 and so on. And so I've actually printed the percentage error. So if I just go to the end of that, we see that the error percentage is 17.5, which isn't great, but it's not bad either. You can try different test and training sets. You can try training on the entire training set, which isn't a great idea, but you can give that a shot as well and see if you can bring this down, try and converge this a little more. What I'm going to do now is I'm going to run this on the entire data set. And why I'm doing that is I want to visualize how it predicts. And so what we have done here is we've said print X-ray 1 and 2, which means the entire data set. But now the color is blue if the prediction is 0 and red if it's 1, right? And why predict test F is this. So what it's done is for each data point in the data set, it's gone in and first got the prediction, then based on whether the y-hat is greater than 0.5, it's actually classified it, right? And we're plotting that. So we see that, as you would expect, it's linear regression, logistic regression, but with like it's logistic regression that's quite simple with the W1x plus W2 and so on. So what it does is it is able to get this class boundary very clearly. You can see this is where the boundary is, and anything to this side is classified as this, anything to this side is classified as red. You take the original data set, you see that there are quite a few points that are overlapping, right? You're seeing that they're overlapping here and here. So clearly it doesn't capture the overlap, and that is where the errors are coming, right? So any data point that is this overlap is being misclassified. But anything that is to this side of this boundary, this classification boundary, is being classified correct, right? Okay, so that is where our error is coming from. And that's kind of the best you can do with logistic regression. So we've seen how logistic regression works, and we've set it up in the form of a neuron, right? So if it's a single neuron model and you're using it for binary classification, meaning two classes, and you're trying to classify it, this is kind of what you will get. Now it's a very powerful approach, and when you get to different kinds of problems, classification problems, it's a good idea to start with just doing a logistic regression in this. You can either use the machine learning model or you can use this as a neuron, and it'll help you understand kind of what or how well you should at least be doing, right? If you can't better this with a more complicated network, then it's not worth doing a more complicated network, right? So we've seen logistic regression from the point of view of a neural network or a neuron. So hopefully that has really helped you out. And now what we're going to do is start assembling networks and look at a slightly more interesting classification problem for that. So hopefully you've learned from this. See you on the next one.